So, all right, we talked about in 14.3, how do you modify that RNA transcript before you then do translation? So what we're doing in 14.4, translation is a process where you take the RNA and translate it into the language of proteins. So let's go over that idea. It says RNA directed synthesis of a polypeptide. Remember, a protein is, like in translation, we're technically making a polypeptide, and that's my best attempts at drawing a polypeptide. But like a protein could be made of like 4, let's say, of these polypeptides, or 2, or 3, or even just 1. So technically, we don't make a fully complete protein in the process of translation. So just kind of keep that in mind, so you're not confused about what they mean, like when they say polypeptide versus protein. All right, so now if I were to add a little detail here, we technically in transcription make mRNA. The M stands for messenger RNA. Well, there's actually 3 different kinds of RNA we use in protein synthesis. We have the messenger RNA, and then we also have these things called tRNA. The T stands for transfer RNA, and this transfers the RNA. It's going to transfer that RNA to what's called a ribosome, and we've talked about the ribosome. You've learned about ribosomes all the way since 7th grade or so. Ribosomes are like protein factories. They are what is going to take the mRNA and use that to make your protein. Okay? So let's get into some of the details of it. So this is, if you really get this slide, you really get all of 14.4, which is, there's a lot of details to it, but the basic idea I don't think is that complex. So here's our messenger RNA that we made. Remember, messenger RNA goes from 5' to 3'. So now we need to read the message. The thing that reads the message and translate that message into your polypeptide. So your polypeptide, these are the amino acids. Remember, we have 20 different amino acids. So these would be different amino acids. We link them together to make a polypeptide. Remember, then that polypeptide folds up into your protein. Okay, so here's how it works. The tRNA, it has 2 ends. On one end, it has the amino acid. So one of 20 amino acids will be attached to a single tRNA. One tRNA transports a specific amino acid. So this tRNA will only transfer glycine. Okay? And at the end of the TR, the other end, you have what's called an anticodon. So you got to remember back to, I believe last class talked about codons. Codons are the language. It's every 3 nucleotides on the mRNA. That's like every 3 nucleotides. That codes for a specific amino acid. I showed you that big chart where you would read like first base, second base, third base to figure out what amino acid went with the codon. Well, the anticodon reads the codon. So it's the name kind of tells you what it does, but it's complementary to the codon. So I don't know if you can see this clearly, but on here it's saying GGC. That's the first, not the first codon, that is a codon on the mRNA. So this anticodon is complementary to that. So car in the garage, CCG would be the anticodon. C would pair with G, C pairs with G, G pairs with C. Okay? So this tRNA, how it knows that in this protein we want to have a glycine amino acid is by the anticodon recognizing that sequence. This CCG always will go with that glycine. So there's only one tRNA that has CCG going with glycine. Okay? All right, so this will go into, there are 3 slots on the ribosome. This is 1 slot, 2nd, and a 3rd. I'll show you some of the other names of them later on, but it'll come into this first slot, and then what will happen is this tRNA, once it binds here, it will then attach this glycine to the previous amino acid in the chain. So here, glycine would get attached, and then this tRNA would move over, and this chain, so this would get attached here, but then this whole chain would be broken from here, from this tRNA, and attached to this tRNA, and this tRNA would become the one that exits. And it's kind of, you picture it like an actual animation, that would be how it happens. And then the next tRNA would come in and read the next codon on the mRNA. Okay, so that's your overview. We'll go through it in more detail each step by step. That's kind of the big picture of translation. That's the short story of it. Okay. All right. Make sure I said everything here. So again, each tRNA goes with a certain amino acid. Okay. Complementary base pairing. Let's talk about the structure of a tRNA. The structure of it's kind of interesting. So this is a tRNA structure, and they call it a clover leaf structure. Where now this exists in 3 dimensions, right? Like we aren't 2-dimensional, but this is like their best attempt to show you a 2-dimensional picture of it. Why it's helpful is you can kind of start to see hydrogen bonding. That's a very common theme in the structure of the tRNA. The tRNA is made of RNA, and it's going to fold on itself. And like what holds the folds in on itself are these hydrogen bonds. So I kind of showed you this idea when I showed you the spliceosome, where the RNA and the spliceosome can recognize specific parts of the intron, like the bases that are complementary to the spliceosome on the intron. A similar thing happens. The part of like a CCAG on the one arm of this tRNA can recognize the GGU on this portion of the tRNA, and that would allow them to stick together. So it has 1, 2, 3, 4 arms, they call it. That's why they call it like a 4-leaf clover. Then there's the 2 ends of the arms I told you about in the last slide. You have the amino acid attachment site, where you would attach the amino acid, and then the anticodon side at the very bottom. You can even think of it almost like a key. It looks a little bit like that. These asterisks, not super important, but just if you're wondering why they're there. Basically, there are some like subtle chemical modifications that can happen to different base pairs that would technically not make this be like, say, an A. Technically, there's other chemical groups on there where they can't just say that's an A. So it's just kind of a fine print sort of detail, but it is something that's there. Okay, so there you go. Basic structure of it. And it's, just to be clear, this started off as a single strand RNA. And then what made it a tRNA is when it folds up into, and I think to point out the obvious, this looks like a T. Right? Yeah. The lowercase t. If you're wondering, it's about 80 nucleotides long. Not overly important. Now in 2 dimensions it looks like a T. Really in 3 dimensions, which I'll show you in the next slide, it looks more like an L. And again, that anticodon, so if I show you the 3-dimensional picture of it, literally looks more like an L. Here's the anticodon. That would recognize the, so there's kind of a good filled in version of it. This would then recognize the codon on the amino acid sequence. Now this is important. Notice how the anticodon goes 3' to 5'. That's because the mRNA it's reading goes 5' to 3'. And then what would be the mRNA that this anticodon goes with? You need to be able to do that. What is complementary to A? Luke? UUC, right. A goes with U, and G goes with C. Okay? And that mRNA would be 5' to 3'. And then you would be able to look up UUC on that codon chart, and that would determine what amino acid goes there. Okay? All right. So I mentioned this before, that we have specific you have a specific tRNA that goes with a specific amino acid. Now, there is an enzyme that will facilitate the binding of an amino acid with the tRNA. That enzyme that facilitates that binding is called aminoacyltRNA synthetase. And I know that sounds like I think some of you just like fell asleep while I was saying that word, right? The word actually says what it does. Like chemistry, conveniently, we're doing, remember a synthesis reaction in chemistry? You take like two elements or two smaller things, more reactants, and you get fewer products. So synthetase, it's taking your reactants, tRNA and amino acid, and it makes one product, the tRNA with the bonded amino acid. Amino is referring to amino acid. Acyl, don't worry about it. It's just some chemical group that's on the amino acid. But that's what the name's going with. And so yeah, it's gonna match the tRNA with the mRNA. Now this third point's kind of interesting. So let me show you the codon chart to help you understand the third point right there. So when I showed you this codon chart, I said I asked you like, hey, what is the mRNA sequence for the amino acid proline? If I asked you to write that down, I said, well, what would be like the issue if I asked you that? Remember what the issue would be? Luke? There are 4 different options, right? Like, which option? Do you want CCU, CCC, CCA, CCG? But notice how the first 2 are always the same. CCC, CCC, CC. So this idea of wobble is this concept that third base can change, but it still codes for proline. So that tRNA, that anticodon on the tRNA would be GG, if we're talking about proline, GG, and if it's this one, it's GGA. But the idea of wobble would say that tRNA GGA on the anticodon that would go with CCU, that anticodon could also recognize CCC or CCA or CCG because there's a little bit of a wobble. It's like really old keys. I remember one time we got locked out of this van and somebody locked the keys in the car and it was like on this like school field trip. And so like the chaperone was like, everybody get your like keys out, you know, and it was like a bunch of like seniors. And
Students, teachers, pardon this interruption. At this time, all students attending the creative writing field trips, please make your way down to the main office. All students attending the creative writing field trip, please make your way down to the front office area at this time. Thank you.
It's like, so kind of creative writers going on field trips? Like, man. Okay, so anyways, old like car doors, there technically is one key for each car, but there's a little bit of a wobble, right? Some keys, and we actually would get back in the van because somebody also happened to have it's like a GMC key for another GMC car, and there was a little bit of a wobble where if we were to jiggle the key just right, you could actually pop the door open. It's the same thing. I know. I don't think it would happen nowadays. You know, you got like keyless cars and stuff, but like here, that's the idea where the third base wobble would say, let's say the tRNA anticodon technically recognizes CCU. It's close enough where that anticodon could also recognize CCC, CCA, CCG. That's what they're saying about that third base wobble. Okay, so that allows you to have one tRNA that could recognize 4 different codons. Okay, all right. Let me show you a picture of how this would work. So here is your tRNA. Now, notice how they call it tire tRNA. Why? What that TYR stands for is that this tRNA is specific for the amino acid tyrosine. The abbreviation for tyrosine is TYR. So these are separate, but we need to attach this tyrosine amino acid to that amino acid end. The enzyme that does this is the aminoacyl tRNA, but it's this enzyme, and this is a key point to key in on, is specific to tyrosine. That's why they call it tyrosyl tRNA synthetase. The category of those enzymes are called aminoacyl tRNA, but if you swap that up, if that amino is referring to tyrosine, it's tyrosyl tRNA synthetase. If I go back to that codon chart, let's say, arginine is the one that we're trying to attach. You would have argylyl, probably, tRNA synthetase. You would have an enzyme specific for the amino acid arginine. Each of the 20 amino acids has a specific synthetase for that amino acid. So these two amino acid and the tRNA, they would then fit into the active site. You remember your kind of vocab for enzymes. Active site is where the magic happens. That's where the catalyzing of the reaction happens. So they go to the active site, and using ATP, so we do it. This is an endergonic reaction. We have to put in energy. You will then get that. They call this a charged tRNA. What they mean by charge is that the amino acid is bonded to the tRNA. And then now this tRNA is ready to do translation and make that protein. Okay. Here's what it would look like in 3 dimensions, if you're into that. And this is important. It's a covalent bond. So the bond holding this together is a covalent bond. But the bond of, like, when this anticodon, here they're saying it's AUA. When this anticodon meets the UAU of the codon on the mRNA, the bond between those would be what? What kind of bond would attach the anticodon to the codon? Hydrogen bond, yeah. So keep those bonds straight. Okay. So make sure I said everything here. Bless you. Okay, so it's actually going over, kind of moving forward, but now that we have like our tRNAs made, we got our mRNA made, now we're going to talk about the ribosome. The ribosome is the thing that's actually making the protein. So the question is, how do we assemble the ribosome on the mRNA? So how that works is there is a specific portion of the ribosome on the mRNA that the ribosome will match up with. Now, when we talk about ribosome, the ribosome is actually made of a large and a small component. The small ribosome recognizes the mRNA. The small ribosome part of the ribosome will bind first to the mRNA, and then the large will bind second. And I'll show you a picture of that happening. It's worth pointing out, I mentioned that we had 3 kinds of RNA. I said mRNA, tRNA, and you may have been wondering what is the third kind. Well, you have rRNA. What does the lowercase r stand for? R is for ribosomal RNA. So our ribosomes, they're made of protein and RNA. Now, the proteins in the ribosome, they mostly play like structural roles. Like it's just kind of like a scaffold to hold the RNA. So the RNA portion of the ribosome, that actually does the catalyzing. That will actually do like the reaction part of making of adding those amino acids to that growing polypeptide. Okay. All right, so let me show you a picture of how this all works. Here's your ribosome. So here's the small subunit. The small subunit binds the mRNA. Notice how the mRNA goes 5', 3'. Then the large subunit comes second. So the polypeptide grows out of the large subunit. The outer portion of the ribosome is made of protein. The interior portion, where all the chemical reactions are happening, that's made of RNA. And then there are 3 sites, bless you, for the ribosome. There is an A site, a P site, and an E site. I'll explain the names of those when I show you a better picture of it, but just so you're just to kind of clue you into that idea. There's 3 different sites for it. That polypeptide would start growing and it exits out the top of the large subunit. And all right, so here's maybe a better model to show you that the ribosome. So here's the small subunit. So on that small subunit, I said the small subunit binds the mRNA. So there's like a little cleft, like a little ridge that will hold the mRNA, like the RNA can like hook into. A little slot where the mRNA can hook into. And then that mRNA binding site, it'll recognize the start codon on the mRNA. And that's how it'll know where to bind. Okay? So it'll bind there. And then the first amino acid will come in. The A site stands for the amino acyl tRNA binding site. So it's a big word, but break it down. Amino acyl tRNA, that's referring to, that could be like the tire acyl tRNA. That would be a tRNA carrying the amino acid tyrosine. That would bind to the A site, so the first one comes in. And then the P site, the P stands for peptide. Because if I go back to that three-dimensional model, the P site is where the polypeptide grows out of. That's where the P comes from. The E stands for exit. Because the exiting tRNA that's delivered its amino acid will then exit from there. And I'll have a better picture kind of showing you all that. But that's just sort of to intro you to that vocabulary. Okay. So here we go. Here's a tRNA coming in. This tRNA would have the next amino acid for the chain. It comes in. The anticodon, that's the very end of the tRNA, it recognizes a codon. And then once these get recognized with each other, that will then catalyze the addition of the amino acid to the carboxyl end. So you need to know the end. For every amino acid, there is a amino end and a carboxyl end of every amino acid. So the amino end is here. Carboxyl end would be like right there. Okay? We add amino acids to the carboxyl end. Here's how you can remember that. If you're adding to the carboxyl, I just picture you just like sitting there, just stuff like this kind of looks like a little bread roll, and breads are made of carbs. You're just like stuffing your face with carbs, like you're just stuffing. You're just adding new amino acids to that growing polypeptide, and then the ending portion, that's the amino end. Okay, all right, and then once this amino acid's added, then you have the exit site where this tRNA, it's going to attach, so these will get bonded with a peptide bond. This tRNA would then move to the E site, and this whole chain would then get attached to this first tRNA, which will move to the P site and have the polypeptide attached, and then the next tRNA comes in with the next amino acid. I'll have a better picture showing you that, but yeah, again, going over the different sites. P site holds the polypeptide chain. A site, that's where the next amino acid in the chain comes in. E site, that's where the discharged tRNA, the tRNA that's already delivered its cargo, delivered its amino acid, is going to leave the ribosome. Okay. All right. In transcription, I said there was initiation, elongation, termination. Translation, there's also those three stages. So that whole process I just explained, we can actually break it up into 3 steps: initiation, elongation, termination. And all of these stages, they actually require other proteins they call them protein factors, that will aid in this process. And like, we need energy to do this. Like, this whole process I'm talking about here, you can imagine it doesn't just happen on accident. You're actually going to need energy in the form of GTP, not ATP, to provide that energy. Remember, hydrolysis of ATP or GTP, that releases energy that we use to do it. So let's do the initiation process. So here's initiation. How it works is you have the initiator tRNA. Now, if you remember when we were going, I said there was one codon I wanted you to remember, and I said it was the initiator one. And when did we start school? August. So AUG, that codon, we met in August. So for every protein, the first amino acid, the initiator tRNA, would be a tRNA carrying methionine. Okay? Everybody loves to ask questions about that. I don't know. I don't really know. I guess it's a poor detail, but like disproportionately, people ask a lot of questions about that. Methionine comes in, binds to. So in other words, the start codon is always AUG. Okay? So then tRNA comes, binds there, And then this will then recruit the using GTP, the AirJ GTP, and other protein factors they're not showing. So in the background, you have a bunch of other proteins that will bring in the large ribosomal subunit so that initiator tRNA can go in the P site and start that polypeptide from growing. Okay, so we call this whole complex of ribosome, NRA, and all the other protein factors helping this to happen the translation initiation complex. Okay, let me make sure I said everything there. It's worth pointing out, like when this mRNA like hooks into this notch, this mRNA will move along, this ribosome will move along, the small ribosomal subunit moves along the mRNA until it finds that start codon. Then that's when it knows, okay, we're in the right spot. Okay, and again, the start codon, why that's important is because it establishes the reading frame. It establishes when do we start reading the mRNA, when do we start reading codons to establish the next amino acid that's going to come in that polypeptide chain. Okay? Large ribosomal subunit, that comes after the small ribosomal subunits come. And then, again, protein initiation factors, other proteins, help facilitate this process. Okay, a lot going on in this slide. This is I know it's kind of hard to read. If you get it on big screen on your computer, it can help you. This is the best resolution I can get. But this is just nothing necessarily new here. This is kind of bringing everything together. So here is our polypeptide. Now, what is this first amino acid called? What would that be if I were to label it? Methionine, right? We met first polypeptide, always methionine. Remember the amino end, that would be the very ending of the chain. Carboxylin, we add polypeptides to the carboxylin. Imagine you're stuffing your face with carbs. Amino acids, the next amino acid comes into the A site. How we know which amino acid, which tRNA comes in, is by recognizing that codon. And this process of attaching this amino acid, forming that peptide bond between this amino acid and the next amino acid in this chain to that carboxylin, you have to use GTP. Then, this is what I was trying to really key in right here, because I was trying to show you that I don't think this was as clear as I was describing earlier. This polypeptide chain was attached to this amino acid. But when you bring in that new amino acid, we want to kick this amino acid out, this old tRNA out. So we have to transfer this chain to this tRNA. And that's what's happening here. We transfer that chain over to this tRNA. So this tRNA will then shift over to the P site. And then, so that's what they're starting to show here. We shifted that chain over, that polypeptide chain over. And this P tRNA moves to the E, the exit site. And now that first tRNA, this tRNA, is now in this position, is in the P site now, and it's holding the polypeptide. And it's ready for the next tRNA that comes in. Okay? And we keep doing that until when? How do you know when to stop? Aditya, what do you think? You look for the stop codon. So somewhere along that amino acid, that mRNA, somewhere on that mRNA is a stop codon. That's how we know when to stop. Which is the next thing to talk about. We call that process of moving this peptide, like moving these tRNAs through, translocation. Translocation is what's happening here and here. That process of moving this tRNA over to the next site. And direction. Notice 5', 3'. We're doing this ribosome is moving along the mRNA from 5' to 3', the same direction that we made the mRNA to begin with. All right, we're almost there. I know this is a lot. I just want to talk about how we finish. So we finish when you hit a stop codon. Somewhere on here, the 3 stop codons, UAG, UAA, UGA. Once you find that on the mRNA, the ribosome finds that, you don't have another tRNA coming in, you have a release factor. So there is a release factor that only recognizes the stop codons, the 3 stop codons. Okay? Once this binds in, this release factor will then cause the addition of water. So you have hydrolysis. This will cause the addition of water to this polypeptide that will break it apart from this tRNA. And then this release factor will then, using energy of GTP, will then cause the large and small ribosomal subunits to break free from the mRNA. Then we know we're done, once you hit that stop codon. Okay? And that's about it. Let me make sure I've said everything real quick. Okay, so I made a mastering bio for this section. It's not due next class. If you wanted to start on it, you can, but I'll give you a little more time next class to work on it.